I'm really looking forward to having a conversation this morning about how to both detect and trust trends. Arguably, one of the most important tasks that we have as environmental scientists is to be able to detect changes in the environment and to be able to explain those changes. But as I'll show this morning, sometimes trends are not always what we think they are, and there may be a host of other factors that we need to take into account to explain what's going on with the data. So Biljana, I'll just try and share my screen now, if that's okay.
Yeah.
Okay. Unfortunately, I can't see the chat box when this happens. So would you be kind enough to let me know if there's any comments as I go?
Yes, I will.
Can you see my slides okay?
Yes, we can see them. Okay.
All right. Well, yes, good morning again. And as the title suggests, I posed this provocative question, like, when is a trend not a trend? What is a true trend? What statistical methods and supporting techniques can we adopt to interpret trends that we see in our data? Yesterday, in my haste to get started, I was rude enough to forget to introduce myself. So I just thought I'd say a few words before I get going to help you understand what makes me tick, where I come from. So I've spent about 30 years working in the area of climate and water science in both academic environments and for government, and in consulting and in full-time research. And this slide here just gives you a flavor of the range of organizations that I've worked for over the years. But I think the common theme that threads through all of this is that I'm really passionate about using environmental data and information and models to support decision making. So I approach the use of data and models from a very much applied and pragmatic point of view, and hopefully that will come across. I'm not formally trained in statistics, although I do use a lot of statistics. So as we get into some of the statistical discussions, you'll see that I adopt a less formal approach than someone like Manfred, who's clearly an expert in time series analysis. So just to explain why there might be a difference in style here. So why is data consistency so important? I'd like to start by referring to a document that was published in the UK about 20 years ago. And this was our nation's first attempt to try to come up with a set of national climate change indicators to describe how the climate and other important aspects of our environment and key sectors like water and farming have been changing through time. And what's interesting about this report is it contains a blend of indicators. So you've got classic indicators like rainfall and temperature. You've got derived indicators to do with soil moisture, and you've got indicators to do with wildfire occurrence. And then you've got some really quite esoteric or strange indicators like how much water is being used to irrigate our potato crop. But the value and the power of these sorts of national indicators comes from our ability to trust in the continuity of those records over many years and decades through time. So we can see whether wildfires are becoming more or less frequent. We can see whether rainfall is going up or down. And I'd be very interested to learn more about whether or not you have a similar set of indicators or are developing the same for Serbia as part of your national decision support systems for climate change. But data consistency is really important to be able to trust any emerging signals or trends that we see in these indicators that may be informing really big investments, for example, in new water infrastructure. So this morning, I'm going to basically provide a non-statistician's definition of data homogeneity, of stationarity, and formal detection and attribution of trends. And then I'm going to give some examples of some tools and tests that are used to identify homogeneity, and also to detect emergent trends and changes in long time series. And then I'm going to move into some more recent research where we've been taking large ensembles of climate model information to try and understand changes in extreme events, but changes in very extreme events. So, for example, how might the 1 in a 100-year rainfall event be changing through time? And clearly that's a really tough question to answer because our data sets are so small or so short. So how can we have confidence in detecting trends in such rare events? And then woven all the way through, I'm hopefully going to be explaining why this really matters. So let me start by posing you a question. Here's one of the most famous climate time series in the UK. It's a time series showing winter rainfall amounts since the 1760s through to the present year. So it includes the last winter. And you can see straight away there's lots of ups and downs in the data from one year to the next. So there's a lot of variability in winter rainfall. But in the UK, there's been this really powerful message that has been coming across from climate centres for a long time, that our winters are getting wetter. Now, my question to you is, if you look at this information I've just put before you, do you think that's a fair assertion? Yes or no? Maybe you have a view on that. What's going on here? So if you've got any thoughts or questions about this time series, then perhaps just drop them in the chat box. Any thoughts? Can we trust this data set of national long-term rainfall changes at the scale of England and Wales? Is the UK becoming wetter? Well, when we dig into the detail, we're having to make assumptions about the continuity of the measuring techniques, the instruments, and the observing network through time. Three really big factors that can influence a long-term trend. And thankfully, in the UK, we benefit from the hard work of past climate scientists like Gordon Manley and Elizabeth Shaw, shown here, who spent years working in archives, looking at diaries of clergy, of farmers, and all sorts of other data sets to try and piece together really long-term records of the UK climate. And until recently, one of Manley's records of long-term snowfall has only just come to light. It's been now digitized and used in the study that I'm going to show next. But you can see here a page photograph from the ledger from Manley's records, handwritten notes on winter snowfall totals. And these are held in the archives at Cambridge University. So took some finding by my friend and colleague Connor Murphy to reconstruct a long-term history of snowfall to help us interpret the changes that we see in the precipitation record. And what we learn from this time series, if we look at the top graphic here, which shows the amount of snow days in southern England, and you can see considerable variability from year to year. But there are these periods in the early 19th century and late 18th century where there was a significantly greater number of snow days. And in fact, we can relate that high incidence of snow days to this potentially dry period in the early part of the record. And when we then try to explain how this rainfall record has evolved through time due to patterns of weather and circulation conditions across the country, what we find is that there's a very, very strong association between the frequency of snowfall days and the residual in that previous rainfall record. So in other words, when we're seeing very dry winters, we're seeing very snowy winters reconstructed from this independent evidence. We bring these two pieces of information together, and now we're able to conclude that actually the early trend that we see in this record, this is all snowfall undercatch. So in fact, when we correct for the snowfall undercatch in this record, when we create a more homogeneous series through time, the trend goes away. So we have now completely revisited and changed our perception of winter rainfall in the UK, of one of variation from decade to decade, but no significant long-term trend once we take into account changes in observing and measurement practices and the occurrence of snowfall, which is much harder to measure in this early period. What we also learn is how sensitive our conclusions about the long-term trends are to the period of record that we study. So we've got, over 200 years of data, 250 years of data. And if we have the start year in the 1800s or the 1750s and the end year in 2000, and we analyze the trends over all of those possible pairs of start year and end year, what we see is this domain of statistically significant trends when we look at the full record, but when we start at a later period where we have more trustworthy data, those trends go away. So we can now begin to say that the historic interpretation of the trend in our rainfall data was purely an artifact of this undercatch in the early period, and that when we disregard these early data or we correct for them, the trend goes away. A similar thing happens for summer rainfall, but this is not obviously to do with snowfall undercatch. This is to do with changes in the network, the number of observing stations recording rainfall at this time, which were only 2 or 3 in the early part of the record, and then a lot more now. So here we think there's a possible undercatch or misrepresentation of the rainfall distributed across the country as a whole in the early record. So from this simple example, we can see how trends just taken at face value really have to be checked out in some detail. Is the network consistent? Is the start and end date appropriate given the quality of the data? And are there any biases in the information through changes in observer practice or instrumentation? So here are the 4 key terms that I'd like to explore this morning. So here I'm saying that a homogeneous data set is one where we have statistically similar properties in space or time. So in the case of the UK rainfall data, we want homogeneous data with similar statistical properties at the beginning and the end of the data set in order to trust the trend. And then secondly, we have stationary data. And yesterday, Manfred gave some really nice formal definitions of stationary and non-stationary time series. In my simple worldview, it's a case of, is the mean and variance constant in time and space? And I'll show you some examples later on. And thirdly, there's this term of detection. Are we able to see or discern or find an underlying trend given very noisy data, dirty and imperfect data? And detection is our ability to basically find a trend or a pattern of change, but we're not attempting to explain it at this stage. We're just saying, is there or is there not a trustworthy trend in the data set? And then fourthly, we have attribution, which is if we find a trend or we don't find a trend, can we explain that? Is there a physical basis for that presence or absence of a trend? And this can be done formally at a certain statistical level. Okay, so let's begin by just thinking about some of the homogeneity tests that can be used. And I'm guessing that these are familiar to some, if not many of you. But just for completeness, I want to just give you a sense of the range of techniques that are out there. So first up, as I was stressing to the PhD students yesterday, there really is no substitution for visually inspecting data to see whether or not there are any step changes or changes in variance or behavior or anything else that raises questions in our mind. So looking visually at the data and applying our expertise is always a good first step. Then we can compare data sets side by side. So if one rainfall series is showing this pattern, what does the rainfall station closest to that record also show? Is it showing similar behavior? If not, that could be a sign that one or both of the data sets are not homogeneous. We can fit regression lines to subsets of the data to see how the trend might change, and that can be used as a test for breakpoints. And the most widely used technique is the Chow test, which basically compares the two trends on two halves of the data with a trend fitted to the whole data set to see whether or not you can better explain the behavior of the data in two trends rather than one. And that's a simple technique to apply. The Buishan and the Petit tests essentially look for drifts in the cumulative anomalies or drifts in the ranking of values through time to see whether there's a maxima in the anomalies or a maxima in the changes in the ranks. And these two can indicate where there's a breakpoint. And then finally, there are much more sophisticated homogeneity tests, which may apply multiple comparisons of series against multiple network of time series across a whole network of stations to see whether or not one record is behaving more or less similarly to other records in the network. And I'll say a little bit about that later as well. So one of the most widely tests that is used for homogeneity is Petit's test. And this basically proceeds in 6 quite straightforward steps, which are possible to code up in Excel and execute very easily with a given time series. So you start with your time series of data, which might have n years of information, which might be n years of rainfall values, let's say. And then you assign a rank to each of those years. And you cumulatively sum those ranks through the time series in step 3, and you calculate the departure of that cumulative rank from the expected accumulation of ranks, which you would expect to see just by chance, essentially. And you find the year in the time series of ranks, cumulative ranks, where the difference between 3 and 4 is at the greatest point, and that indicates where there's the largest departure between the observed ranking and the expected ranking, and hence where we think with greatest confidence there might be a break point in the data. And then finally, we assess the statistical significance of the difference between those two ranked series using this simple equation here. And it's a very powerful test, and as I say, quickly implemented. So here, for example, going back to the England and Wales precipitation series, I've applied the Petit test through the whole record that I showed you before. And what's very nice about this is it actually picks up a statistically significant breakpoint around 1865. Now that number, that date in the 1860s is significant to us in the UK, because that's when we started to standardize our rain gauges. So before here, you had all sorts of different designs of rain gauges and different qualities of measurement, especially for snowfall, as I've already mentioned. And you have this period of very cold, snowy winters, so a high chance of under measuring snowfall. And then from the 1860s onwards, we have our standard rain gauge, which has pretty much stayed the same since, and much more confidence. So here's a lovely example of how Petit's test completely corroborates the view that there has been a lack of homogeneity in the England and Wales precipitation series. And so we must really be very cautious about how we use these data in the early 1860s. Now, I was curious to see how Petit might apply to Belgrade, and so I took the information that's in the public domain from the global summary of the day and looked at how maximum temperatures and minimum temperatures have changed through time. And the data I could find only begins in the 1980s, so you can see quite a lot of variation. Obviously, a very clear warming trend in both the annual maximum and the annual minimum. So things are definitely getting much warmer in Belgrade than they were 30, 40 years ago. But this is a really nice example to show you, because it provides a cautionary remark. And my question to you now, and this I'd really like to have some dialogue, if you'd like to feed back to me, is, do you think when you look at these results that this represents a break in the homogeneity or something else going on in the data? How can we explain perhaps this difference between the earlier period and the later period? Any thoughts on whether or not we even trust this as a breakpoint in the data set? So Biljana, if there are any thoughts, that would be great.
There's nothing in the chat, but I can tell you my opinion if you like.
Thank you. Yeah, please do.
I think that this can be a homogeneity bias, because the difference between two periods is quite large. It's more than 1 degree Celsius, which is really, really large, and it breaks in just one point. It's not gradual. But on the other hand, during the last 20 years, we have seen here a lot of extreme events. But bearing in mind that you took this data from global summary of the day, and that we know that these data are biased and have some mistakes and everything, I think that this can be a break in homogeneity, not test of trend and breakpoint in trend.
Okay, thank you very much for those thoughts. So lots there. So the first question is, do we actually trust the data to start with? And yesterday's exercise, we showed how these public data sets do contain all sorts of biases and errors. So we need to be very careful about the extremes, especially, that are being captured in these time series. Secondly, I think you acknowledge the fact that extremes have been increasing across Serbia, across the UK, across North America, in lots of different places. So our expectation is that the extreme values should be going up. There's a sense that the climate regime regionally and globally is changing. But the fact that there is this step change that is statistically significant, so this raised questions in my mind, and I turned to some really interesting literature here. Which, by the way, for everyone listening, if you click on any of these links in your slides, it will take you directly to the papers that I'm referring to. So Busick and von Storch, and this much later paper, they do a lovely critique of Petit's test. So they're putting aside, do we trust the data? Do we expect changes in extremes? And saying, okay, well, what might be some of the shortcomings of the Petit test? And what we actually learn is that that you can find a breakpoint if there's an underlying trend in the data, if there's strong serial correlation, and serial correlation within the data set. So this breakpoint here could also be explained by the limitations of the actual homogeneity test itself, which is known to be not that great in circumstances where there are strong trends or serial correlation. So those of you who are thinking of using this test in your research, I really encourage you to look at these two lovely papers, which provide an honest appraisal of the things you need to be aware of with the Petit's test. And they say that, for example, these tests are most likely to find a breakpoint if the actual breakpoint occurs in the middle of the series rather than at the beginning or the end. So there's other considerations with this test as well. Okay, but I think the Belgrade data provides a nice example to provoke our thinking about the trustworthiness of this test. There are also these, as I mentioned before, much more formal techniques of both homogenizing and testing for homogeneity within time series by comparing across a much wider swathe of stations rather than on a single site at a time, which is how we adopt the Petit's test. And again, I would like to refer you to this really nice paper which illustrates very well how these different homogeneity methods compare when applied to the same data set. And in this case, the data set is 300 rainfall records across the island of Ireland. And what they've done here is in these four methods is to say how often this technique, for example, Homer, finds that of those 300 series, how many of them are regarded as homogeneous. So Homer thinks that 250 of those records are homogeneous. So if you use the Homer test or package, you'd come away thinking, oh, okay, all my data sets looking in good shape. I can trust its homogeneity except for 50 of these stations where the technique shows there's one or more breaks in the data. Now, on the other hand, these other techniques, ACMAN and AHOPS, they show much fewer stations that we would regard as homogeneous and detect many more breakpoints. Just to cut to the conclusions of the paper, the authors in the end recommend the Climatol detection package as one that strikes this balance between over detecting too many breaks or under detecting. So I really encourage those of you who are interested in homogeneity tests to look at this, because it provides a nice summary of the 4 techniques, how they compare in a really rigorous analysis of trends and homogeneity of rainfall across the island of Ireland. And so it provides a really practical steer on which of these techniques or tools you might apply in particular circumstances. Okay, so that's homogeneity. Now let's start to think about time series that are homogeneous. So we trust that the properties are constant through time in terms of the measurement techniques and the continuity of the data set, but they're nonetheless non-stationary through time. And here's a nice example where you have these 2 circumstances where these are rainfall records and temperature records across a swathe of Central Asia. And what the authors did here was to correlate the temperature records that you can see here, which have been standardized. And this is the correlation matrix. And we see that between these stations, there's a very high degree of correlation. They're all behaving by and large in a similar fashion. There's a high correlation coefficient, which is generally a good indication of data homogeneity, because all of these series are tending to behave in a similar fashion. But then using this technique of fitting regression lines to all of the data or later data, parts of the data, we can see some non-stationary behavior. We can see that the rate of warming appears to have increased in the last 20 or 30 years of the time series. So this is a good example to show that, yes, you can have apparently homogeneous data, but at the same time non-stationary data. And in a sense, that's what we're looking for. We want a homogeneous data set in terms of its quality and its consistency, but maybe the ability also to show non-stationary properties, such as the response to climate change. And here in simple graphical form is to help us understand the difference between the stationary and the non-stationary series. So here's what I was saying before. In my non-statistical language, I'd be saying, here we've got a constant mean and a constant variance in this stationary time series. Here that we have a condition of non-constant mean but constant variance, non-constant mean but constant variance with a step change, and a shift in variance but constant mean. So different types of non-stationarity. And those of you who are again looking for an overview of the literature on non-stationary series and their analysis within the realm of hydrology and climatology, I encourage you to look at this review paper led by Louise Slater at Oxford University, in which we have tried to undertake a really comprehensive review of the literature on non-stationary series, their detection and attribution, and a whole raft of other aspects. And you might find that as a really helpful sort of introductory paper that really sets the scene of the literature as a whole. That's currently in final revision at the moment. Just before we move to a little break, I'd just like to, you know, start to plant this idea of, can we explain non-stationary behavior? Because there's one thing is to be able to detect non-stationary behavior, but the authenticity, the trustworthiness of that non-stationary behavior is magnified when we can explain it physically. And I'll be saying more about that later after the break. But here, for example, is a lovely paper by Sorg et al. In which they collated information on long-term mass balance of glaciers in Central Asia. And you know, this is a rather depressing signal, but one that we see all over the world, where glacier mass is reducing as temperature and precipitation changes, and glaciers are shrinking and in retreat by and large globally. So this is you know, consistent with what we'd expect in a warming and in some cases drying climate scenario. And consistent with that are that as the glaciers melt, we have this perhaps short-term bonus period where there is going to be more runoff, more meltwater in the rivers during the present time. And that's what we see. Again, we can see non-stationary river flows, but the pattern of change is by and large consistent with what we'd expect of the shrinking glaciers. And here we also see that the timing of the peak melt has moved forward and is going to continue to move forward. So the peak runoff period is now in this particular part of Tajikistan a month or so earlier than it was a few decades ago, because the temperatures are higher and the melt season is beginning earlier. And so there's been a non-stationary response evidenced by the timing of the onset of the melt season. So again, it's all internally consistent patterns of change. So that builds our confidence in what's going on. But then we start to come into some, you know, some sort of complicated divergence here when we're thinking about, okay, that's the past. How's this going to play out in the future? So if we look at a mass balance model of glacier and snow change, we just see this gradual retraction of the snow mass, and through time, an expected fall in river flow. So a point will come, according to this particular model, where there'll be little or no snow and ice left, and little or no meltwater in the future. However, other models which don't treat the ice as a static block, but as a fluid, are able to sustain that melt at lower elevations for longer into the future. So we now have a model here which shows that the peak time of melting might not occur until the end of the century in the case of these particular glaciers. So both of them are exhibiting clearly non-stationary behavior, but we have two very different views of how a glacier should be treated or modeled under climate change conditions. And these different views of non-stationary behavior bring us to a really important debate that's going on across Central Asia and other parts of the world, where hydropower and water supply for agriculture and industry and people is potentially falling away, is reducing with climate change as the glaciers melt. So again, here, perhaps a question to the group is, from your understanding of glacial behavior in Central Europe, what's our expectation of the non-stationary behavior? Do you think that this graph here describes the glacial reserves, the behavior through time across Central Europe? Have we reached peak water? Has the amount of meltwater from the glaciers reached the maximum? So are we looking at non-stationary behavior following an upward trajectory? Still, are we still in phase one? Are we perhaps at the turning point where our expectation now is that the time series should show a flattening of glacial runoff? Or have we entered phase two, where glaciers are now so much in retreat that the meltwater is expected to fall away? So I hope you can see from this example that our interpretation of the non-stationary behavior in this really critical case depends on our worldview. Are we in phase one, phase two, or somewhere in between? And it shows the link, the connection between the analysis of the time series and the conceptual model, the theory that we have in the back of our mind that's going on to explain the behavior. So I'd be just very interested to hear your reactions to this based on what you know of glaciers across Europe. Do you think we're in phase one, phase two, or at the tipping point? So what would be our expectation?
There's nothing in the chat, but we are probably at the, in my opinion, it doesn't have to be right, but probably at the tipping point now, because when we looked at your previous slide with the models and everything, yes, we can probably be at the tipping point right now in the Central Europe due to the different projections of temperature increases in this part of Europe for the next 20 years, probably.
Yeah, thank you for that. And but I hope you can see the importance of where we sit on this theoretical curve in terms of interpretation of the non-stationary behavior, in terms of the physics. And I think this is actually a critical research question, not just for Central Asia, but for us Europeans. You know, what is happening to the snow and ice across Europe? Are we in phase one, phase two, or at the tipping point? Because where we are at this point in time has critical implications for the long-term management, maintenance, and upgrading, retrofitting of infrastructure across our continent. So I just put that there. This is, you know, big stuff, why time series analysis like this, homogeneous records, really matter. Okay, I think that's perhaps a good point at which to take a 5-minute break to stretch our legs. If in those 5 minutes you've got any questions or thoughts that you'd like to pose, then please put them in the chat box and we'll pick them up on our return. But let's just take a break then. Okay.
Okay. See you in 5.
See you in 5. Okay, welcome back. We good to start again?
I think that we are okay. I think maybe just a minute more. Nobody's okay. There is Dean. I'll just ask everybody to turn their cameras on.
Okay, thank you.
Okay, we can start.
So were there any questions or comments to begin with?
In the chat, nothing.
No. Okay. All right then. Let's continue with this. So here's an extremely difficult question to answer scientifically, and one which is, I think, just as important in Central and Eastern Europe as it is in the UK. So how are very rare extreme events changing? So we're not just talking about changes in the mean or changes in annual statistics. We're talking about how have the really big damaging events changed through time. And this image here, for example, shows you what a 1 in 100 year rainfall event looks like in the UK. This was a huge flood event associated with Storm Desmond in 2015, in which parts of the northwest UK received more than 300 millimeters of rainfall in 24 hours. And based on available statistics and data, it was estimated that this was a 1 in 100 year event. But the question it poses is, we know the climate is changing. Is this event, is the severity of the 1 in 100 year event going to increase in coming decades? And if so, how do we accommodate that in our infrastructure to protect people's homes and businesses from changes in extreme rainfall? So it's a really important question, but obviously one that is extremely technically challenging to answer, because most of us have only got a few decades of rainfall data to work with. So our confidence in even the estimation of the present 100-year extreme event is pretty small. So what I'd like to do is to introduce you to a new approach that's being developed, and I'm referring here to one of my PhD students' work, Timo Calder, who's just published his work in one of the nature journals on this technique called unprecedented simulated extreme ensemble approach, or unseen approach. And it's essentially a technique for exploring changes in these really rare events within modeled worlds. So, and then we're not using the modeled worlds of a conventional climate model. We're using the modeled worlds of seasonal forecasts or weather forecasting systems, where there may be a large number of ensembles or groups of forecasts that are produced by these systems that we bring together. We pull the data to essentially increase the size of the sample, and then the estimation of these extremes. And Timo began his research by exploring, for example, how the autumn 3-day rainfall total in Western Norway and Svalbard has changed through time. And he's focused on autumn 3-day rainfall because these are historically the most damaging events. So when you have 100, 200 millimeters of rainfall in these regions over 3 days, then there's likely to be significant consequences for infrastructure and people. And I'm guessing that in Serbia and elsewhere, we could also sort of ask the question, what are the most damaging events? What are our cities and landscapes vulnerable to? And use that as the indicator that we're going to explore in this sort of extreme event analysis. So for Norway, you can see in the blue crosses the limited amount of observed data. So that's showing how that autumn 3-day total has varied through time. So, and there's about 40 years of data. So to estimate the 1 in 200 year event for design purposes from 40 years of data is clearly extrapolating way beyond the realms of the data set, and you're on really shaky ground doing that kind of thing. But with these large ensembles of climate model experiments, you can start to attach confidence intervals to how those types of extremes have evolved through time. But you can't use the climate model information in its raw sense. You have to do a bit of work first to make that climate model information appropriate to the spatial scale of analysis. And this rather complicated figure just shows how this is done. So you're having to, first of all, take all of these different realizations from the seasonal forecasting system, which is producing information several months out in time for 25 ensemble members. So each line here represents a different ensemble member. And we're doing that for 4 months out ahead of time. So you end up with actually an ensemble of 100 members from which you can extract the maximum values as we've got here. And with that, you can then look to see how those maxima vary through time across the different ensemble members, because you want them to be uncorrelated. You want those maxima to be uncorrelated, so you then maximize the sample size. As I'm sure many of you appreciate it, where data sets are correlated, the effective sample size is much smaller. So one of the early tests you have to do is to look at the correlation between these ensemble members and confirm that they are, most of them, statistically insignificant. So we can treat each ensemble member as a plausible representation of reality, as an independent representation of reality, albeit within the model world. And you also want to check that when you pull these data from 2, 3, 4, or 5 months into the future from this forecasting system, that the pulled data has similar properties. And we can check for that by producing these empirical probability density functions for each of these time periods, 2, 3, 4, and 5 months ahead. And you can see how stable this is, that the distribution seems to be independent of the time series, the forecast horizon. So another check that says it's okay to pour all of these data into the same bucket and treat them as independent values, independent extremes. And we can also look at how these different ensemble distributions, how they can compare when we look at the return period estimates as well. But because this is operating at a climate model scale and the data are at a much finer resolution, we do have to apply some bias correction to take the raw climate model information and make it look much more like the observed data. So some bias correction has to be implemented, and here we're seeing that we can correct the mean. We can by and large correct the standard deviation. The blue bar shows the bias corrected against the observed value in the yellow, and here you can see the other properties, the skewness and the kurtosis, are also preserved. So we're now starting to say that we can pull the data and we can actually interpret the bias corrected information as representative statistically of the behavior at the local scales of interest. And now with this super ensemble, we can actually start to provide an estimate of how that extreme event, here I'm showing the 1 in 100 year autumn 3-day rainfall total, and how that's changed through time in Norway and Svalbard. And so here again, we've got the observed data in the blue, which would show our best estimate based on the observations, compared with the best estimate from the unseen technique, which both of them are showing a trend, but the unseen technique has much smaller uncertainty bounds. So there's, because of the larger sample size, we're much more confident about the underlying trend. And here we can see again the return period estimates. And here West Svalbard, where we don't actually have the observed data, but we can compare how the size distribution was in the 1980s with how it is now, and we can see this statistical uplift of the extreme events. So this provides, you know, an interesting technique to then go back and say, well, what is the 1 in 100 year event, and how has that changed through time? And this final graphic on the technique basically shows, if we'd got the observations and we were just relying on that alone, we've got the blue shaded area and the blue curve, and here are the dots. And because we've only got 30 or 40 years of data, once we get beyond that, the uncertainty envelope explodes as we get to the 100-year estimate, and the 1,000-year estimate is huge, the uncertainty. This is what we would get if we took the weather forecast model without bias correcting it. So because we've got the much larger sample, we can go to these very rare events and estimate what the 1 in 1,000 year event might be. But we can clearly see there's a bias between here and here. And so the final curve, the yellow one, is where the data were bias corrected and then compared against the observations. You can see that they actually match pretty well within the realm of the historic data. But of course, because of the large sample, we've got much bigger data, much more information to estimate these very rare events up here. And this is being used increasingly to think about how the extremes might be changing through time, and to also to revisit some of the extreme value estimates that engineers might be using. Are our design standards sufficiently robust when we take this kind of information and recompute, for instance, what the 1 in 100 year event is? And you can see in this case, the 1 in 100 from the unseen technique is much larger. It is outside the envelope of what we would estimate from the historic data. So that all sounds fine, and for those of you who are interested, Team Ho has created this workflow that is in the public domain, where you can search different data sets and apply these checks for the consistency and the bias and the stability of the data. And he demonstrates this, for example, using the Siberian heat wave, the recent heat wave, and showing how estimates of that can be revisited using these very large ensembles. But the question here is, you know, from what I've just explained to you, and maybe it's the first time you've come across the unseen technique, is, are these values unseen but physically possible in a model world where different circumstances and combinations of circulation and land surface come together to create an extreme event? Or are we having to rely so much on the climate model realism and the bias correction? Are they still unrealistic extremes? And that's the tension that exists with this this set of techniques? Are they unseen but plausible, or are they unrealistic because they've been generated by a climate model? So again, I just put that out there, and I just raise that question and ask if anyone's got thoughts or reactions to what I've just shown you. Has anyone come across this technique before, or is this all new?
There's nothing in the chat. I probably know.
Okay, all right. Well, Biljana, you seem to be the spokesperson for today, so I'm going to put you on the spot. What was your reaction to what I've just shown you?
Unseen or unrealistic.
Yeah.
In 2004, we had a similar situation here in the Balkan Peninsula when we had extreme precipitations and extreme flooding. So I don't think that we should say that they are unrealistic. Maybe they're just not they're just unseen, and probably in the future we will see more of these extreme events based on our knowledge for the past 20 years, probably, as far as we can remember. Things are getting more extreme here. Maybe it's because of the climate change, probably, but also because of the infrastructure that is not well equipped and not well, how to say, we don't keep it well. We don't invest a lot of money in the infrastructure of, I don't know, riverbeds and small riverbeds. So it can probably be the combination of both. I don't think that these events are unrealistic. We can expect the extreme events like 2015 in UK and 2014 in Balkan Peninsula, but will they come sooner or later? We have to rely on the models and estimates. So that's my opinion.
Yeah, I think it's a good thing to keep an open mind, isn't it, about just how extreme can extremes become. And these modeled worlds allow us to imagine plausible extreme events that would seriously test our infrastructure and our systems. So I think if nothing else, these techniques provide a very powerful thought experiment to challenge engineers and government about, have we got high enough standards for designs? Are we investing enough in upgrading and maintaining existing infrastructure? So it provides a very powerful set of information to challenge any complacency that we might have about our existing systems. Okay, I got just about 20 minutes or so to go, and I'd like to just cover a couple more concepts which I think are helpful to understand. And one of them is this idea of the time of emergence concept, and it's one that the media in particular are often quite interested in. Is, you know, when will we see a climate change signal? When will we be sure that there is a climate change signal in our data set? And Ed Hawkins provides this really, I think, workable definition. So it's the time at which the signal of the climate change is essentially bigger than the noise of natural variability. So, and we can capture that statistically by comparing the changes in the mean or the trend against the changes in the variance in the data. And that's exactly what King et al. Did on a global scale, looking at patterns of emergence of extreme events using standard indices, which would be familiar to many of us. So seasonal means, JJA for summer, and seasonal mean temperature in winter, DJF. Maximum temperature in summer, maximum temperature in winter, minimum temperature in summer, minimum in winter, mean summer rainfall, mean winter rainfall, and the 1-day annual maximum rainfall in summer or in winter. And just, it's a lovely paper in which they look across the globe using those 10 indicators to try to identify when and where the climate change signal emerges first, using this time of emergence concept. And basically where you're seeing the reds and the oranges and the yellow, well, let's concentrate on the reds and the oranges. Those are the parts of the world where a climate change signal has already emerged from the background noise of climate variability. And so, for example, summer temperatures in the tropics are already outside the range of variability. So according to the authors here, climate change signal is already detectable in these vast swathes of the tropics and large parts of the southern hemisphere. And you can see that applies across Australia as well. But turning now to the much noisier rainfall series and extreme rainfall, on the other hand, we see more blues and purples. And you can see that based on the climate model projections, we're not expecting to see any emergence of a climate change signal in our part of the world until the second half of the 21st century. So sorry, this is too small to zoom in on Serbia and too small really to see the UK, but you trust me, there's a lot of blues here, or even greys, because climate change is unlikely to be detectable at these smaller scales because of the large interannual variability in these extreme events, such as the annual maximum rainfall total. But it's an interesting idea, and some 15 years ago, I was curious enough to say, okay, I wonder when and where climate change might be first detectable in the UK in terms of rainfall and river flow records. And fortunately at the time, there was this really nice paper published by Ziegler et al. that set out a quite simple statistical method of comparing the trend against the variation in the data set and against the confidence intervals that you want, the certainty that you want in your detection level. So this is to essentially avoid a type 1 error and a type 2 error by specifying levels of detection in this part of the equation. And this paper, lays out this method in a really straightforward way that even I was able to implement, and it was a really helpful paper to get into detection times if you're interested in that. So I took that approach and looked at river flows where for different types of catchment across the UK, representing different types of geological conditions, different catchment sizes, different locations around the country. And I was curious, how is there this trade-off between the strength of the trend that we expect from climate model projections versus how long is it going to take for us to be able to detect a change in the river flow? And for the vast majority of the rivers in the UK, the answer is we're not going to be able to detect a climate change signal in our river flows this century. There's too much variability from one year to the next, and the expected climate change scenario, the signal is too small relative to the very large variability. But there's one exception. There's one type of river catchment where this could be the case, and this is where the rivers have a very, very large groundwater component. So the river flow varies much less from one year to another. So the river flow, like in this catchment, which comes from chalk geology, has very little variation from one year to the next. And now we can see that when a climate model projection is saying a 30% change in the river flow, which is in the range of some of our projections, could be detectable in these sorts of rivers within 20 or 25 years of the data, depending on whether we base our estimate of the variance of the flows on this 30-year period or a much longer period of record. So this sort of analysis is potentially helpful to policymakers and managers, because it can start to tell us which of the river basins we could use as an early warning. So which of the rivers should we be paying really careful attention to detect the climate change signal first? And the analysis points to these rivers in southern England as perhaps what we would say the canary in the mine, the bird that's going to scream first. We've got climate change going on here. And we can do the same for the detection time for changes in rainfall. And there's a lot of detail in this table. Basically, we can break England and Wales down into different homogeneous rainfall regions and look for when the detection time might be in the 10-year one-day winter rainfall, or the 50-year one-day winter rainfall, or the 10-day winter total with 10-year return periods. So you can look at different kinds of indicator here, and basically we increase the chance of detecting a climate change signal if we go to these longer averaging periods. So we're more likely to see a signal in the 10-day total in some regions. We can compare these two, but the 1 day versus the 10-day, because that again damps down a lot of the variability. So multi-day extremes give us a greater chance of detecting a climate change signal than single-day extremes or short duration extremes, because of the smaller variability. And again, we're able to identify parts of the country in southeast England, southern and southwest England, where if the climate models are right about the expected rainfall change, these are the parts of the world, parts of our world, where we would expect to see the climate change signal first. Now, this was published 10 years ago, and some of these results here are suggesting we should see the climate change, should have seen it already. So if I had the time and I was a super scholar, I would love to go back and repeat this analysis with the actual data to see whether or not what we predicted 10 years ago has actually happened. But I just present this as again, it may be an interesting thing for you to apply in your region using data sets to answer that question: when and where might we see climate change first, and which are the most powerful indices of extreme events that maximize our chance of finding that signal. Okay, final part now, and this is perhaps the most difficult bit. We find a trend, we find a change. Can we explain it? And here, you know, the great scientific challenge is to relate cause and effect. And so my final remarks then are really about how we attribute or explain a trend when we found it. And the likely candidates, the likely causes of the observed trend are going to depend on the scale of the analysis. So if we're seeing trends at daily, annual, or decadal, or longer periods, or if we're seeing changes at the scale of a small river basin through to large catchment regions, a whole continent, or the globe, we're going to be looking at for different candidate variables. And this is, again, I refer you back to the Slater et al. Paper, where we discuss the likely drivers of trends at different time and space scales. So this is a useful starting point to recognize that we're looking for different explanatory variables at different time and space scales within this overarching framework. And yesterday, I referred to this case study in which we did just this for trying to interpret long-term changes in mean and extreme river flows in the River Boyne in Ireland. And this is a very important water supply catchment. So what happens in this catchment has big implications for water security in the eastern part of Ireland. And in the paper by Harrigan et al., we start by making the case for setting up working hypotheses. And this is how I think this is the most robust and defensible approach for climate change attribution, is to write down as many hypotheses as you can imagine to explain the change. Okay, so we as a group in the authors of this paper, we came up with about 10 or 11 ideas to explain what I've just shown you here. What could have caused this jump? And these were the ideas. So like I've suggested earlier, is it because the data are poor quality or untrustworthy? Have there been major water diversions or exchanges, water imports to this catchment? Has water been moved from one part of the catchment to another? Has urbanization affected the hydrology? What about the amount of forestry, drainage, and the agricultural land use? And so you go on. And basically, with these hypotheses, you can then look for the supporting data. You can start to set up a range of modeling and statistical tests to begin to eliminate them. So if we've done a good job with quality assurance, we can say, okay, we're confident that the data sets are homogeneous and that the change is a true change. So we can throw away that hypothesis and narrow the candidates to explain the change. But some of these ones that are in here, shown in the green, do require quite sophisticated hydrological modeling, because the only way we can test this hypothesis is within the hydrological model world. So we took hydrological models, we changed the properties in the model, we calibrated them on one period and then tested them on another to see whether or not it was changes in rainfall or changes in land cover. And basically, through these hydrological models, we can see here the simulation between the observed and the reconstructed simulated flows here is a good match in the start of the record. So if we calibrate the data, calibrate the model on this period, and then run it forward in time, we see a big departure between the hydrological model and the observations. So that raises the question, is that because the hydrological model is poor, or is something else changed? Has something changed at this point, this change point that was detected by the Petit test, which we also ran and showed a break point in the mid-1970s? And basically, you know, the only thing that we could do, the only things that could explain that change was the coincident expansion of the drainage of the fields, as I think I mentioned yesterday. So that's changed the relationship between the rainfall and the drainage of moisture from the fields. There's also been changes in the agricultural land use. The changes in the rainfall. Rainfall has gone up because of the North Atlantic oscillation has been in a positive phase. And we think there's also the possibility that these factors are interacting with one another. So we actually concluded that the step change that we see here is real. It's not an artifact of the data. It's most likely driven by the drainage, the expansion and change in drainage, and a change in the rainfall. But I present this example because it offers an overarching framework in how we might go about attributing hydrological change or changes in extreme events. And you can see here, again, quite substantial shifts in the hydrology here, accounted for, in our view, by those 3 or 4 factors, not operating in isolation, but in concert with one another. Okay, then, just to sum up then and to finish, I hope that I've shown this morning that trends can arise from a range of factors. It can be simply that the data are poor, they're not homogeneous, or it can be just natural variability that creates a short-lived apparent trend. So the key message from today is really we need to have a conceptual model or a good physical explanation for why that change is happening. And that means we need to turn to independent data to check the trends and the drivers of the trends. We need to refer to metadata and use this information to really test whether or not we have a credible explanation for the trends that we are seeing through time. I've closed also by showing that when we apply time of emergence and detection techniques, actually we don't expect to see a climate change signal at many space and time scales. We have to be really smart about the data sets, the indicators, and the time and space scales that we work at if we're serious about detecting an expected climate change signal. And hopefully some of the techniques I've shown you would be useful and helpful to do that. So finally, what's the recommended reading? I really strongly encourage you, those of you who are interested in homogenization techniques, to go to the Cole paper, which, as I showed, compares these different methods and provides a really nice summary of the strengths and weaknesses of those methods. EXtreme, I didn't have time to talk about today, but is a thorough review of lots of different types of hydroclimatic index and their fitness for evaluating change. So that's a nice summary there. Timo Kelder, that's the paper on the unseen trends and the unseen methodology. Slater is the review of the non-stationarity literature and approaches. And then finally, there's this paper by some bloke called Wilby, who was curious enough to look for when and where climate change might appear in UK river flows. So on that point, I'll just close and invite any questions or comments.
You can write your questions in the chat as well, if you're not really familiar, or if you're not comfortable talking, you can use the chat, and we can read the question and answer it now or in the afternoon session. Also, if you have any questions for Rob, you can ask him, and on the 5th day he will give you an answer and explain everything that may be a trouble for you. So please do not hesitate to ask. It will be good, because we as organizers of the event cannot think of everything. So we would appreciate if you could think of some scientific question and ask instead of us, because we are all over the place at the moment. So thank you for that. If there aren't any questions now, we can have a break, have lunch, and come back at 4. And then Rob will help us with some online data sets and tools, and we can have a practical session. We have one question, sorry. Xenia said, oh, it's not a question, great presentation. Thank you very much for very useful references.
Thank you very much for the feedback. I'm wondering, you know, I hope what I've presented to you before was there was some new material, some new content in there that you hadn't come across, and that I haven't just told you what you already knew. That would be terrible.
No, for us, for me, it is something completely new, and I look forward to doing some similar analysis with you on this project, and hopefully someone from the team here and in this workshop will join us in the future, and we will have a joint publication together, or maybe some scientific project. We'll see. I really hope for a good networking after this.
Yeah. Well, I think if no one has done it already, I think just to apply some of the detection time and emergence analyses for you know, your part of Europe would be really interesting to see what's going on there.
That's why we need colleagues from the region, from Bosnia, from Croatia, because we need the data and we can make some good things together. But collecting the data is actually the most difficult assignment. But afterwards, we can have a rewarding and good scientific paper. Yes. So if there aren't any questions, we can come back here at 4 and do some data quiz.
Yeah.
Okay. Thank you very much for this.
Bye then. Okay. Bye then.
Bye. Bye, everyone. Thank you.
Good afternoon, everybody. I hope you are okay and ready for another session. Professor Rob Wilby will help us with the exploration of selected online data sets and tools, and we will have some data quiz and try to find data errors and biases. So please, Rob, the floor is yours.
Okay, thank you very much. Let me just try again to upload my slides. Okay, is that good? Can you see? All right, I'll keep it this format because then I can also meanwhile see people as well, which is nice. Makes me feel like I'm speaking to an audience. Okay, so welcome back, everyone. This morning we were thinking about data homogeneity and also thinking about different techniques for detecting climate change signals in data sets using a range of indices and emergence statistics. This afternoon, I'd like to do two things. One is to have a quick quiz to see how well we all understood what we were covering this morning and to sort of reinforce some of the points. And then I've designed a short exercise which will hopefully illustrate how we can use homogeneity testing to find spurious data, but concentrating now on spatial arrangements rather than time series. So using this comparison of data sets as a basis for homogeneity testing. So this morning we covered 4 key concepts. This idea of homogeneity, which in my non-statistical world I define as a data set where there's consistent methods of measurement, consistent instruments, consistent observers, and so forth. So we're looking for homogeneous records with which to discern is in the environment. And then we have the second concept to do with stationarity. And as I mentioned, Manfred has already given you all a very detailed and rich set of statistical definitions for the term stationarity. Again, I take a sort of a simpler approach of looking for shifts in the mean and or the variance in a data set, whether in space or time, as a working definition. Then thirdly, the idea of detection, And this is about how can we find a climate change signal despite the fact that the environment is inherently variable, highly variable. So we're looking for a relatively small signal of change, often within a lot of variability year to year or place to place in the environment. And here we're just trying to say, is there a signal or not? And is this due to something that we can explain is changing in the wider environment? And then finally, the hardest step is to actually explain any trend or signal that we've discerned from the data set. And we can do that statistically using confidence levels, or we can do that in other ways, indirectly using modeling techniques like hydrological models to simulate worlds with and without certain driving conditions. And I gave you an example from the River Boyne as to how we do that with multiple working hypotheses. So hopefully that captures roughly what we did this morning. There was some extra new research in there on the unseen technique as an emerging approach for analyzing very rare and extreme events, but in modeled worlds, where we're looking for plausible combinations of physical processes in the atmosphere and the land surface that can generate really extreme events. In fact, events that are more extreme than we can yet find in even the longest of historical records. Now then, let's see how much of all of that was captured as I spoke this morning. So I've got a quiz here with 5 questions, multiple choice, and let's see how we all score. So first question then. Data homogeneity is important for avoiding non-stationarity in data, reliable change detection, attributing the cause of change, all of the above. Now, as with the researchers yesterday, I'm encouraging you to chat with your neighbor for 20 or 30 seconds to see if you can arrive at a shared view on what the correct answer might be. Off you go. If you'd like to use the chat box to enter your choice, and then as this morning, Liana, if you could just let me know what the consensus view is, and I won't put you on the spot.
The majority of people in the chat said B. The answer.
Very good. Reliable change detection. So of course, we
also there are some D's here.
Okay, that's okay. B's the correct answer. We don't necessarily want a homogeneous data set to avoid non-stationarity, because there may be a truly non-stationary signal within your homogeneous data set. We could have the same instrument, the same observer, the same site recording temperature over 200 years, and it would be non-stationary because of rising air temperatures. But we do want a homogeneous record so that we can say that if there is a change, whether it's a step, a change in the mean, a change in the variance, that is a true change, not an artifact of any of the observing, measurement, or instrument issues that I've mentioned before. And you don't necessarily need a homogeneous data set to describe the causes of change. We could have a non-homogeneous record with a step change, because we know that there's been a change in the location of the observing station or the river gauge. So we can explain the non-homogeneity without it, without having to have a homogeneous record. So it sounds like the majority of you got the right answer at B. Let's see how you get on with question 2. The non-parametric Petit test for breakpoints in a time series is sensitive to the magnitude of the shift and record length. And by shift, I mean the step change. Or do you think it's sensitive to serial correlation and trends in the data, or the amount of variability in the data, or all of the above? Again, if you'd like to enter into the chat box what you think the answer might be, that would be good.
There are A is the majority said A, magnitude of the shift and the length, record length.
Okay, let's take a look. Oops, there we go. D is actually all of the above. And this is why with even a simple test like Petit, we have to be quite careful how we use the test, when and where we use it. Like all statistical tests, it comes with assumptions, and its power to detect a change varies. It's more likely to be able to detect a change if there's a big step change, and if the change is in the middle of the record. It is sensitive to serial correlation and trends in the data, and one is advised against using the test when we have this. And obviously, the noisier the data set, the harder it is to discern a true step change in the data. I mean, it's in a way, there are very, when we see a time series like this above, which is for rainfall over the Sahel, which is perhaps one of the most famous climatological step changes, where we see this dramatic drop in rainfall across the Sahel in the late 1960s, early 1970s. That's a really clear and abrupt regime shift here. And so obviously there's, fitting a linear trend through that is meaningless, but there's something very large, and there's lots of theories about why that rainfall has changed so abruptly over the Sahel. And the Petit test is perfect in this kind of situation. Okay, whoops, let's go to the next question. Question 3, which of the following are stationary time series? Annual global mean surface temperature, annual global mean sea level, Earth's radiative energy balance, none of the above. Same thing, see what you think, and please enter that into the box.
Now I see everyone is answering D, none of the above.
Correct, none of the above. All right, so they are all examples of non-stationary series, and hopefully all of those really important records of global change are homogeneous records. So the measurements are being produced and created in a consistent way, allowing us to say with confidence that the non-stationarity that we see is a real thing. Okay, question 4. This is a tricky one. The time of emergence for an anthropogenic climate change signal is earliest for summer low flows in UK rivers, summer mean temperatures in the tropics, winter maximum one-day rainfall totals in Serbia, or winter minimum temperatures in Australia. What do you think it is?
Everyone's saying B.
Everyone's saying B. Absolutely. That's, you remember that the study that I referred to, the global study, is a really nice analysis of all of these types of indicator. And you remember that I said this morning that tropical temperatures, the climate change signal, emerged there very early in the 20th century. So that's where we're most confident of a change. Okay, very good. So it seems like everyone's got 4 out of 4 so far, or near enough. Let's see how you do on the last question. The unprecedented simulated extremes ensemble unseen approach can be used to A, investigate atmospheric conditions leading to weather extremes that have not yet been observed, create super ensembles of extreme events from climate forecasts spanning many seasons ahead, simulate highly localized extreme convective storms, specify engineering standards directly. Which is true? I should issue a bonus point for this question. It's a hard one.
So far, we have 2 answers A. Then the third one is A also. Okay. Everyone's saying A.
Everyone is saying A.
Now, Teen and Minucher are saying B. Then A. Then A. Then B.
Pressure's on now. Then a bit of a split decision here. Okay. All right. Well, the correct answer is A. It's an approach that helps us to consider extreme events that have yet to be seen. But I stress that these are within modeled worlds, which we know are imperfect representations of the true world. It's not B because we can only group together these ensembles so many months out into the future. If we go too far into the future, the boundary forcing effects from ocean temperatures and ice extent and things like that start to provide a consistent signal across the different ensemble members. So we can no longer treat them as independent, which is necessary for the pooling of the data sets. We can't use this for highly localized extreme rainfall events because these convective processes are just not represented within the weather forecasting models. So even with bias correction, you can't really correct for a process that isn't actually in the model in the first place. And related to that, D, we can't really use this information for design standards directly, but we might ultimately be able to use this information for designing if we can apply bias correction, but only to certain types of extreme event. And we still need to be a bit cautious about extremes such as sub-daily rainfall totals, but we could be more confident about these larger scale rainfall phenomena that may create floods generated over 1, 2, 3, 4 or 5 days over longer periods, much more confident. Okay. There we go. So answer A is correct. Did anyone get 5 out of 5? All right. I'd be disappointed if everyone got 5 out of 5. It means we've got to stretch everyone a little bit. Okay, so now I'd like to just give you a little bit of background to this homogeneity exercise, and I'm going to be referring to recent research into long-term changes in water temperature, something which I know is something that there's an interest shared by a number of us in the group. So as you may appreciate, globally, river water temperatures are rising and are expected to rise in the future. Why do we care about that? Well, water temperature is a primary driver of all sorts of ecosystem functions and of water quality and water reactions, chemical reactions. Rising water temperatures, for example, may threaten those species that throughout recent history have thrived in cooler water conditions. Higher temperatures can also exacerbate certain types of pollution issues. So rising water temperatures globally is something that all nations should really be taking seriously. And it is something that is expected to become more extreme in coming decades. Now, a few years ago, this group of researchers looked at rising water temperatures in the Danube. And what we've got is the maximum and the minimum temperatures shown on the left and the right, respectively. The black lines show the water temperature change, and the blue lines show the changes in river flow. So what strikes me when I revisit this these graphics, is that river water temperatures are rising in all three of these sites, both in terms of the maxima and the minima. And these changes are happening largely independently of changes in the river flow, although there are some links between the two. The other thing is that the changes seem to be more sensitive higher up the river you go. And Biljana will remind us that there seems to be a nice connection here between the North Atlantic oscillation driving year-to-year variability and the longer-term trend in the water temperature. So we've got, really nice causal mechanism to explain why temperatures are higher in some years than others, related to the warmth of the winter and also to the amount of rainfall and hence river flow that occurs during certain winters. So it all hangs together really nicely. And I just show you this to bring home the message that water temperatures is something that we care about all over the world. Now, in the UK, we've been trying to look at changes in river water temperature at very fine spatial resolutions to see what the thermal footprint might be over the UK in terms of the evolution of water temperatures over the last 2 or 3 decades. The problem we have is that the network that has been used to measure water temperatures has changed dramatically. And this is a real statistical headache when, for example, you can see how many monitoring stations there were in 2001. And we can break these monitoring stations down. We can count them by sub-region of the authorities that manage water across the UK, across England and Wales, although we've just got the results here for England. So there were a lot of stations in 2001. 2018, not only have we got fewer stations, so the richness of the data set is less, some of the stations have moved, or there are new stations have been introduced and old ones have been taken out. So the networks aren't in 2018 an exact subset of 2001. So statistically, we've got non-homogeneous data here in terms of the network coverage, its density, and the location of the stations. That's the first headache. So this is a really great example of a non-homogeneous record. The second headache we've got, and this is one that I explained to the early career researchers yesterday, is that the time of sampling at many of these stations has changed through time. So you may appreciate that river water temperature is monitored by going to the site, literally sometimes throwing a bucket over a bridge, pulling the water out, putting a thermometer in the bucket and measuring the temperature. And
we were asked if you could use a slideshow option because it would be easier for the participants to read from the slides.
Here we go.
Okay, thank you.
How's that? Let me just go to the duplicate slideshow. How's that?
Now we okay. This is great. Thank you.
That's good, is it? Excellent. Okay, thank you. So as I was saying, on this axis, this is the time of day. So 8 o'clock, 10 o'clock, 12 o'clock, 2 in the afternoon, and this is the year. And this time of the day denotes the time when the field officer went to the river, collected the water from the river, put the thermometer in the water, in the bucket, and wrote down the temperature. And crudely speaking, in the late 1990s, the field officer was going and taking the water temperature at breakfast time, and then coming forward to the latter part of the record, the technician was taking the water temperature at lunchtime. So we, of course, expect water temperatures in the river to be higher at lunchtime than they are earlier in the day and at breakfast time. So this gradual drift in sampling later in the day has also introduced a non-homogeneity within the record. So not only is the distribution of sites changing, when the technician went to the site and took the field measurement has also changed through time. So that's created another headache for us. So what we've ended up doing is, for each year, taking all of the available stations and correcting the temperatures to a midday value. So we were using a regression relationship between the measured temperature and the time of day, and then correcting everything to midday so that it's all comparable. We haven't attempted to account for the changing distribution or number of stations in this network. And you can see gradually through time, as we go from 2001 to 2018, you have fewer stations. But what you can see through the color coding is, if you squint, if you close your eyes a little bit, you can see that there are certain hotspots of rivers, you know, around this area in the east of England, which consistently stand out as warmer areas. And there are also other places which, you know, are consistently cooler, sort of higher ground, and so forth. And through analyzing this spatial data in relation to other things like geology and altitude, catchment area, and things like that, we're able to explain why the temperatures appear to vary across the country at a national level. And all of this is heading in one direction. This is my hope. If I manage to publish one paper this year, it's on the creation of a simple national water temperature index for England. So to combine all of that information into a homogeneous but clearly non-stationary record of water temperature change in winter, spring, summer, and autumn. And we've done that by not trying to meld all of the data across all of the network, but by selecting those stations that are most representative of the country as a whole, or of key regions where we're seeing most rapid change in water temperature. And that is allowing us to go back to the 1970s, not as early as you've been able to do in the Danube, which I think goes back to the 60s or even earlier. The earliest we can get to is about 1970 in England. But here we go. Here's some provisional results which are showing the temperature change through time. Now, as I move towards the exercise, you're wondering what's coming over the hill next. Those national maps hide an enormous amount of detail of what's going on at an individual catchment area. And about 10 years ago, I set up this field experiment where we installed water temperature tiny tags in the river, like here. We can see one of my field assistants working here to install the equipment. And we also hid them in trees on the north side of the trees, so they're nice and shaded. That's not an exactly perfect setup, because ideally the temperature device would be installed in a proper shaded environment, but then there's a higher chance of interference or theft of the device because it would stand out. It wouldn't be just concealed in a tree. So we have to trade that off. But we established what probably at the time was one of the most dense water and air temperature sampling networks in the country, to really understand how and why water temperature is varying within this catchment, and how that might impact the fish and the bugs in the stream and the plants and other things that we care about. And what we did through field experiments and from trials with big pools of water in my own garden, where we put these tiny tags in tanks and sometimes left them shaded or unshaded, and then compared the results between shaded and unshaded tags. So we've got the gray line is where the tag has been shaded, and the black line is where it's been exposed, so when to direct sunlight. And when you look at this axis, they don't look very different, but when you look at the right hand axis, then the difference between these curves, you can see that you can get an error of 1 degree or more if a tag is exposed to direct sunlight in a tank in my garden. And actually in the field, we suspect that there are bigger biases if these tags haven't been carefully located, or if sometimes in the day or during the year, they're exposed to direct sunshine. So the task I've set you this afternoon is to look at the Excel data set, which we will turn to shortly. And I would like you to just simply tell me which, if any, of the 6 sites in this data set are suspect. Are there problems to do with the exposure of the tiny tag, time of measurement, or whatever? But you've got 6 time series of water temperature taken from this system, and you can see very different sorts of environment. So D1 is in the headwaters of the catchment, so very hard to find a shaded location here. D6 is in a quite narrow valley, 10 likewise, and then we come further downstream to where there's a strong influence from spring water, groundwater, making the water temperatures cooler in certain parts of the river. And then D22 is right at the lowest point, or towards the lower point of the system that we were monitoring. And each of these photos you can see in kilometers. That's the distance from the source. So a little bit smaller than the Danube in terms of the length of the river. So we're talking less than 30 kilometers from the headwater to the outlet of this river. but nonetheless, there's some very interesting and large changes going on in the water temperature within this system. So the task I've set you is laid out here. It's to open the Excel file called Luton Tmax, and to first of all visually inspect the data to see if anything stands out straight away. And then I've suggested a number of steps that you could take as part of this homogeneity exercise. Now, Biljana, I wonder if we can all just confirm that everyone has got the Excel file and understands what the task is.
We sent this morning the link to the shared folder with the reading material and the Excel file. I hope that everyone got it this morning, but if not, I can resend it. I think you already received an email this morning around maybe 8:30.
Okay, so if everyone can just open that file, and you know, so no one's feeling under pressure here. What I'd suggest we do is that it's 25 to 5 your side. Let's give ourselves 25 minutes to just look at these data in your own time in a relaxed way, and just try and figure out what's going on within the data. And then the answer is there a problem in these data, and if so, which of the sites that we should be concerned with? Is that clear?
Yes.
What I'll do is I will stay online. I'll turn my camera off, but I'll try and get the chat box back up somehow. And if anyone's got a question, or perhaps you can just speak over the over Zoom and just raise the question with me as we go along. I mean, I'm sorry I can't be there to help you interactively, but I think this is probably the best way to do it, is if I let you alone for 20 minutes or so to have a look at the data, but I'm standing by if anyone's unclear. How's that sound?
Good. Nice. Thank you.
All right. So
everyone agrees.
Okay. So see you back at 5 o'clock your time for the answers. All right. Okay. Okay, folks, just 5 minutes to go, and then we'll share our findings. Okay, 5 minutes. With 1, 2 or more sites, then perhaps you could just type that into the group chat. Okay, early bid there for a D1 and D16. Okay, all right, there's some consistency coming here. Has very high temperatures, yeah. Good, yeah. Oh, someone thinks D6 as well. Who is that? Is it, sorry, but the pronunciation, is it Dushanka? Sanka?
Just to check once, because my kids are around me.
Okay, let's come. So most of you think D1, most of you think D16, and some of you think D6. Let's see how that plays out then. So I'll just go back to the full screen show now, just to help you see things. Okay. So I think, as I've been stressing today and yesterday, a really great starting place is always a straightforward visual inspection of data when the sample or the data set is as small as this. And straight away, as I think most of you picked up, there are clear differences between D1 and D16 and the neighboring sites. So here, for example, 21 degrees 0.6 compared with 15, and then higher again here at D16. And the interesting pattern that has emerged here is that these high anomalies tend to occur on the warmer days. So we can look down and we can see a cooler day, 10.8, and there's much less difference. So on this particular day, D1, which is the highest elevation site, which we would expect to be the coolest, is actually the coolest. And then the river gets broadly warmer as you go downstream. So what might be the causes of these anomalies? If you could, rather than use chat box, just turn your microphone on and speak, that would be really helpful.
As you said in the beginning, D1 is the in the area where there is no shade.
So let me just remind you what these sites look like.
Source of the river and no shaded areas to locate the sensors. That's
it. Yeah, we, with the best will in the world, we are struggling to find a good site to install the air temperature device in this kind of environment, because this is relatively high altitude for the UK, 300 or 400 meters above sea level. maybe a little bit higher, there's bare cover here, moorland, and we're struggling to find shade. So what we're seeing here is essentially the effect of direct sunshine onto an instrument that can't be shaded. And so the temperatures are, the anomalies are greater on the hot sunny days than they are presumably here. This was a cold, grey, maybe even rainy day where there's little or no sunshine at that on this particular day, so little or no influence. So visual inspection gets us a long way there in terms of discerning where there might be problems in the data. Likewise, some of you might have calculated some basic summary statistics, and you know, the mean is higher at that top site than ones further downstream, yet we would expect the ones downstream to be becoming progressively warmer. But the difference is most marked in the actual maximum recorded. So 33.3 degrees C here, and everything else apart from D16 is around about the 25 degrees mark. So several degrees warmer than neighboring sites should be ringing alarm bells in our mind. There seems to be less of a problem with the minimum because that's obviously occurring at night. So there's little or no, no influence from solar radiation, obviously, but there may be other local thermal effects in certain situations that could lift the minimum at night. But also the standard deviation is a helpful indicator, because if there is an erratic signal due to direct sunshine exposure on some days and not on others, then that would show up in a larger standard deviation. So we can see that here D1 and D16 stand out. Now, I think one or two of you thought that D6 might have a problem as well, and I'd be really interested to hear why you think that's the case. Now, I've got an open mind on this. I'm willing to be persuaded. So whoever entered D6, would you like to just share with us why you think there's a problem?
Well, the case number 142.
Okay.
Just to check if it's... No, 148.
Okay.
It has a slightly higher value compared to the joint average mean value.
Okay.
So I set up the threshold to the 5 degrees plus minus mean value.
Ah, okay. So that's interesting. So you found one particular outlier that didn't seem to fit the pattern, but were there other outliers in D6, or was that the only one, do you think?
The only one.
Okay, so
according to my threshold.
Yeah, well, that's a really interesting approach, and I like the idea there, because what you could then do is go back to the other information, the metadata, check diaries to see maybe that was the day in which the data download was undertaken and there was some corruption of the data or some interference of the tag as we removed it to download the data. Perhaps we inadvertently exposed it to sunlight at that point. So flagging up even these occasional outliers is all useful stuff for improving the overall homogeneity of the data. And then scatter plots as well. Broadly speaking, where you see the cloud looking wider apart, more diffuse, that's where we might have a problem. So in the opposite case, here we can see D10 versus D6. Maybe here is maybe this is that outlier for D6 that was mentioned earlier, which was for some reason much cooler than expected. Maybe that's the one that you found. But overall, we can see a nice correlation between those two neighboring sites, apart from that one outlier point. And we compare that with when we compare D1 against the same site, D10, or D1 against the lowest one, we can see much more scatter in the data, suggesting a weaker correspondence between the sites. In fact, that is confirmed when we undertake the correlation between those sites, and we can see some of the lowest correlations here for D1 here, slightly lower here, but it's sort of less persuasive, the correlation matrix, than I think the analysis of the overall summary statistics, which I think in some ways are very helpful, along with the visual inspection of the data. And one final thing we could do is to actually plot cumulative degree days to see if there's any overall systematic bias. And although the colors don't show up particularly well, here we see D16 in the purple, and it's showing much more degree days than, for example, D22, which is further downstream. So we'd expect that to be the other way round. So this is accumulating more heat here. And the interesting thing as well is that really there's little difference in the winter and early spring, but then as we get into the springtime and the summer, as the sunshine becomes more intense, the difference between these curves grows, supporting our view that there could be overexposure of some of these tiny tags within the network. We also see, well, D1 is in here as well. That's accumulating too much heat as well, is also too warm. So there we go. I think well done, everyone. You saw that even with these fairly rudimentary, these fairly simple techniques, we can quickly establish in just 20 minutes where there might be a problem in this observing network. And then that helps us to concentrate effort on resolving the issues in the field, in the information flow, to reduce the problems, and hence strengthen our trust in any long-term trends in the data that we may see. So just to sort of bring things to a conclusion, here are 3 questions that I thought we might just quickly discuss. So let's say we think there's a problem with D1 and D16. What would be the advice to the field technicians? So that's my first question. And again, if you'd like to unmute and share your thoughts with the group, that'd be great.
Oh, we have in the chat, we have put gorgeous in shade. Measurement standardized for all sites at 7 a.m.
Yeah, actually that is I'd never thought of that one. It's an obvious one when you suggest it. Why not standardize all the temperature measurements before essentially sunrise, if you can, to avoid the direct solar influence? That's a really great idea. One I hadn't thought of, but I will take away from the workshop. Thank you for whoever suggested that. Okay, so standardization to earlier times of the day, shielding those sites, the tags, or trying to relocate them. Yes, I agree with that. But again, the difficulty we have is that you can imagine this is quite a remote area. We have permission from the farmer to locate the equipment on his or her land. But there's often, walkers and other people in the area. So most people, 99% of people will leave experimental equipment alone, but there's always someone who's a bit curious and might interfere with the equipment. So keeping the equipment in a good place scientifically, as well as keeping it concealed and shielded, is often a difficult thing to do. So that's why we didn't choose to go for a very elaborate shield for the device. But I like the idea of standardizing to earlier in the day. All right. What else? What other rules could we do to speed up the process for detecting problematic data? I think someone suggested earlier, having this sort of 5-degree threshold as a rule of thumb. And I think that's a really great idea. Anything else?
We have here standardization of all sites and reduction of directly solar radiation.
Okay. I'm thinking now in terms of the steps. Once we've downloaded the data, we've got the data archive. What simple methods could we use? Quality assurance techniques could we use to flag up potential issues with the data?
We have here plot everything.
Sorry.
Plot everything. Yes.
Yeah, you're speaking to my heart here. I just think there is, no substitute for just visual inspection of the data, plotting the data. It sounds terribly simple, but at the end of the day, these are often the most effective ways of spotting problems and outliers. But we might automate it by, as someone suggested, having a threshold check with neighboring values. We could try to see whether there are biases in certain times of the year. When are the differences greatest across the network, and that might highlight particular issues. But I think the threshold check is probably the simplest way of doing this, looking at all the neighboring sites up and down the network. Okay, then the final question then, and this is probably the hardest one. Let's say we found these suspect values in D1. What am I to do with this data set? Do I throw away these numbers? Do I put a missing data code in its place? Do I take the average of the neighboring ones, or use some other approach to counter these known errors or these suspect values? What should I do?
Dušanka said exclude them.
Okay, so if I exclude them, obviously I'm not going to put, from yesterday, I'm not going to put a 0 there. I'm going to use some missing data code, aren't I, to register that. But then once I start to exclude the data, that affects things like calculation of seasonal averages.
We have count again or compare to others, check with neighboring sites, interpolation.
Yeah, so one way of resolving that would be to create a regression relationship with a neighboring site where we trust the values. and then use that regression relationship to estimate what that value should be. So if we think that D10 is a good site and we think that most of these values are okay, we could use the value on this day to predict what this value would have been if there'd not been any interference by the sunshine. So we would expect, given that this is higher than D6, we might expect a temperature of, I don't know, about 14 degrees or high 14 degrees Celsius on that particular day. And maybe we can predict it from the best sites that we have. There is no right or wrong answer for this. It depends on, again, what the purpose of the study is. If having a full data set to calculate a seasonal mean is necessary and you've got lots of gaps in the data, then filling in using a neighboring site is one option. The alternative is just to neglect that site in your analysis and just refer to the sites that are trustworthy, but then you are throwing away useful information. So alternatively, you might be able to build a nice relationship between the air temperature and the water temperature, and infer from some other physical property what that should be. So there are a number of techniques, and it depends on the ultimate goal of the study. Okay, then. Well, I hope you found that that was a useful little exercise, and again, just makes the message that we don't necessarily have to implement really sophisticated techniques to identify and address some quite obvious problems with our data, and that we can use relatively simple methods to identify the data, the suspect values. So to just sum up what we've tried to do in the last 2 days, we've looked at the hydromet information flow from the setting up of an observing network, the purpose of that network, and the various things we can do to do with quality assuring the data at each step in the process. And for those of you that weren't at the primer session yesterday morning, I think that's been recorded and the slides are available if you like to look at what I'm talking about here in terms of the information flow from beginning to end. And, you know, always being skeptical in a healthy way about the quality of our data, especially when we're using data that have been gathered by someone else, where we might not fully understand the limitations of the information. And I've given you a sense of some of the simple tricks of the trade, as I call them, for finding problematic data and for detecting any of these issues in data sets. And today we've been looking at why we need to pay attention to data quality, especially if we're working in the field of environmental change. Because at the end of the day, we want to be absolutely sure that the changes that we're seeing in our data reflect real changes in the environment and not an artifact of our measurement techniques, our networks, our instruments, and our observers. So I think that's a good point to end. And I'd just like to remind everyone that this is part of a long-term collaboration. I'm really looking forward to the discussions at the end of the week when we start to swap ideas about possible collaborative research projects. I hope today I've dropped some really big hints as to where I think there could be some exciting opportunities to work together in your region. If you've got any further questions or comments in the light of today, or you'd like to follow up on any of the points or the sources that I mentioned, then please get in touch. I think, what is it now? Nearly 4:30 5 for you. I think you've all earned an earlier day and an earlier finish. So handing back to you now then. Okay. Thank you.
Thank you, Rob, very much. But I have a question, if I may. And okay, Alexander can ask first, yes, and then I will ask. Okay.
Thank you so much, Professor Rob, and thank you so much, Biljana. Hi, my apologies because I didn't have internet connection in the morning, but now is better. I have very interesting question maybe, and before I would ask you, I would just say special thanks to you because excellent lecturers and very, very interesting topics.
Thank you very much. That's very kind of you.
Yes, of course. You're welcome always. And also, I have some historical meteorological data, very rare, in some region of Serbia on the south, between 1895 and 1955. But there are still 7 years of measured data missing. And in which way we can find any trend equation or something similar, because 7 years of measured data is, I suppose, is a long period. Thank you.
Okay, thank you for that question. In fact, that reminds me of some work that I did myself a few years ago, where I had exactly the same problem, where I was trying to build a really, really long rainfall record for one of the wettest parts of the UK. And I had pieces of data from this period, from here, from here, from here. So scraps, as I would call them, scraps of data. And what we did was find periods where, with neighboring stations, you have overlapping data. So you have periods where you overlap and you can develop a relationship and start to bridge together the different pieces of data. Just like if you're familiar with tree ring analysis, when people take a piece of timber from this building, this bog, this field, and they find overlapping areas of tree rings. Exactly the same we can do with rainfall, river flow, and climatic data. Now, it's not as perfect as having the continuous record. So that's one thing we can do, is bridge with a neighboring site. And if you get in touch with me, I can send you examples of papers where we've done that. And it's a very simple method. The second technique, which is the one that we used to test the homogeneity of the England and Wales rainfall record, was to find an independent variable, like an atmospheric circulation variable, an atmospheric pattern, and relate that to the variables we were interested in, which might be rainfall, it might be floods, river flows. So you use the weather patterns, for which here in the UK, we've got weather pattern data going back to 1860, but I know that now over the whole of Europe, with the new era reanalysis data sets, there's reconstructions going back a long way. So you can use weather patterns to correlate with your variable of interest to then infill the missing bits. So you correlate against the data you have and then infill that way. And again, I can send you an example where we've done that to reconstruct very long flood histories and to fill in missing data, gaps of data in flood records. So there's 2 ideas for you that might help.
Thank you for answering me, and I will send you. Thank you so much.
Okay, you're welcome.
Okay, I have just one comment for this data from 1850, I think Alexander said. Now I'm reading in a newspaper that we had 100th anniversary of using a new calendar, Gregorian calendar in Serbia. It was officially in use from January 1919. So I think that you should probably also think about the change in the calendar. So the dates before 1919 will be dates according to Julian calendar, and dates after January 1919 will be according to Gregorian calendar. So this also should be taken into account.
Yeah,
thank you for answer.
I was talking about that with Minuter and Teen, and this is what we were discussing, and now I remember that again. Yes.
Yeah.
Thank you for answer.
I should add that, you know, change of the calendar. I should add that to my list of things to look for in the very long archives, because you're absolutely right. That could be an issue in some parts of the world. Because
when we transferred from Julian calendar to Gregorian, we lost 13 days.
Yeah.
So in the record, you will be missing 13 days from the 28th of January in 1990.
Yes, of course.
So,
I suppose, but we will check. Thank you.
Yeah. Okay.
I wanted to ask about the threshold. How do you determine what is the threshold when you look at the suspicious data? How do you determine the value?
Yeah, well, I think yesterday I mentioned that one, rule of thumb that people use is so many standard deviations from the mean. So depending on how strict you want to be, you might go for 3 or 4 standard deviations. To really, 2 standard deviations from the mean captures 95% of the data. So that means you're flagging up 5% of data as potentially suspicious, which is a lot of data in a big archive. So some say let's go to 3 standard deviations, which is 99%, and that means you're just flagging up 1% of the data as potentially outliers. So the 3 or even the 4 standard deviations from the mean is a useful first step. And that's assuming that the data are normally distributed. If they're not normally distributed, then you might go for a percentile threshold. You might say, I'm going to look at the highest and lowest half percentile at either end of the distribution. But I think, people have tried to come up with general rules about this, but you have to be flexible in the face of different types of data, different types of variability, different distributions. But just being flexible and applying a certain amount of common sense, but also, as I said today, what is the expected value? What is a reasonable temperature to observe, or a reasonable flow? So you might even be able to do it that way, in terms of a threshold that is either physically impossible in a location or just beyond the realms of plausibility.